Hello and welcome, folks. This is lecture 21. Uh, Actually, the final lecture I'll be giving this quarter. So we're going to have three course meetings next week, but there are going to be ones where I'm not lecturing, right? So on Monday, we're going to have the pleasure of Chris Leary from Google come down to visit us, and that'll be great. And then Wednesday and Friday is student presentations and final projects, which is always super exciting. So it should be an action-packed week. So this is the last lecture I get to give, so a little sad. It's always fun to do this course. So what are we covering today? What we're covering is hardware intermediate representations, or IR for short. Uh, this is a pretty cool capability, which, thinking beyond this course, what's possible, enables you to make your own hardware tools, right? That's a kind of cool point. So thinking beyond this, what if I make your own hardware language? What if I make your own hardware tools? Appreciating an IR, that's what you do that, right? So specifically, we're going to cover today. I'm going to talk about, why I'm so excited about hardware IRs. We're talking about Fertile, which is the hardware IR inside the Chisel world. We'll actually dive into it and look at it a fair amount, give an example design, show some example projects that actually have used Fertile. And then I'm going to talk more about the exciting landscape of IRs. And this is something that kind of keeps changing every year. So I actually added some new content this year because it's constantly changing. Okay, so like I said, there actually is some code later on, so you can go ahead and fire up a notebook. So we saw this on Wednesday, and here's yet again, let's remind us what we're doing, right? We are, with these hardware generators we're writing in Chisel, we're using programming in Scala to orchestrate hardware instantiation, right? We're declaring components and connecting them together. And so the whole point of these hardware generators is allow us to automate constructing hardware. And so then our users of these generators can simply instantiate them, put the right parameters in, they're good. And so one of the challenges of a hardware generator, and you all learned this in your project, is if you try to be a really robust, flexible generator, sometimes it's not easy, right? Sometimes there's some things you want to support for your users, and that combination of parameters or that particular option isn't super easy, right? And you got to try to imagine all these scenarios, right? And so this is a form of meta programming, right? Where you are writing a program to in a way, program itself, right? Or change its program, right? That's what we're doing to generators. And so to really understand the problem, understand how you're going about solving the problem, and kind of put it all together. And you spend all this effort to figure some of these things out. There's this really challenging problems you're solving inside your generators to do all this. And you put all that, brain power into this artifact, but now it's locked inside your generator, right? So you spend all this time building this thing, and it's only in that generator. And if someone has a similar problem, they can look at your code, but what is the way to kind of share that insight, right? And so, in particular, imagine you work really hard, you make an optimization, and you want to use it on other generators, right? How can you take an optimization from one generator and use that on another generator? Well, you could be really clever and try to do it mostly in Scala, being very sneaky about that. You could use some specific features like generic types, maybe class inheritance, and so. This is possible. Now, what are the caveats to this? Well, if you're trying to use this technique, you're going to at least need to modify the generators trying to use the optimization, if not even the design using this. And, as a person trying to make this reusable optimization, you need to really understand the pattern you're capturing and really make sure it makes sense. And you know what? For some optimizations, this is definitely possible. For other optimizations, this is going to be hard. And let's say you succeed at doing this, which I can believe you can in some cases. What's going to happen? Well, great. Someone's already generated, you know what? I want to use your optimization and this other optimization. And how do you compose these two optimizations together that don't even know about each other, right? Ooh, that's going to get hard, right? And so, to kind of summarize this, why is this hard? And the reason is that trying to make an optimization that's able to work on any generator is a really hard, undefined problem. It's too big of an interface, right? In other words, what's the input? Well, the input's basically a Scala program, right? That's too wild, too untamed, right? It's too hard to deal with. So what's the alternative? What if we can maybe think of another way to package it up, right? So what if instead of trying to integrate optimization into the Scala program that Chisel that does the generation, what if instead we just write the generator the way we write the generator, And then after the design exists, go ahead and modify the design, perform the optimization. That's the key idea. So if you think about that, that could greatly simplify the use case, right? You can write a generator the way you want to write the generator. Don't even need to think about the optimization. And then after the generation's been done, you then call the optimization to then modify your design to do what needs to be done, right? And so this actually does help a lot of ways. Number one, the generator user who's trying to take advantage of optimization, this is much simpler. But also, you solve the composability compatibility issue, right? Where now, if you want to do multiple optimizations, they can be run one after the other, and that's just fine because in this case, what we're doing is rather having the input being arbitrary Scala, the input's now a hardware design, which is a much more constrained item. And because it's much more constrained, it's much more trackable back to write code for this, right? And so as a result, when depending on optimization or transformation you're trying to do in your hardware design, sometimes it's better done as a tool rather than actually doing it in your original chisel design, right? And as a result, you can keep the chisel more straightforward, and then you make this tool that does the thing you want to do, and that tool can be reused across other designs. And so the cool thing is, when you have a tool like this, you don't need to change design to use the tool. You just write the design the way you expect, push it through, and then you run the tool and you need to run the tool. And so what's fun about this is, right, that it really kind of blurs the line between writing the hardware design and running a tool. And you can kind of see the kind of spectrum between the two, right? Where if you're writing vanilla Verilog, right, you're writing a single instance. And in this course, I've said, you know what, we're going to write hardware generators. So now you write, a parameterized meta-program, the ability to kind of generate different instances. Sure. And now we're saying, you know what, maybe there's more sophisticated transformations you want to do design and just being parameterized. Rather than making a super, super complicated generator, you could instead make a tool that does the thing you want to do. And this is going to be much more reusable. And also sometimes that tool, by virtue of design fully existing, may have more information we'll optimize even better. So that's kind of the goal we're trying to do. Cool. Any questions, comments so far? Yes. So yeah, why do I keep saying metaprogramming? How does it mean? Yeah, good question. So in C++ is probably the most common time people otherwise say metaprogramming, right? So it's like templating. So in C++ templates is an example of metaprogramming. You are writing a program, and at first glance, looks like a program, right? What's the difference? The difference is there's kind of this notion of different execution contexts or runs, where it's like the template stuff is supposed to happen at compile time versus the other stuff happens once the program exists. And so the templating, in a way, is specializing that program at compile time, so when the program actually is running, it's a different program. That's the point of templating, is that's the metaprogramming. So that's what we're doing in hardware, is we're not just making a single instance, we are specializing the instance as the program is running. And so the metaprogramming in Chisel is the fact you're using Scala to, as desired, call the Chisel operations, right? If you had straight line Chisel without any, function calls, for loops, functional programming, I would argue you're not really doing metaprogramming, you're just programming, right? But if you actually start using Scala to impact the control flow and that stuff, then you have the metaprogram, then you're kind of doing that stuff. Cool, great question. Okay, so within our complexity, implementation difficulty trade-off plot, right? So imagine you start off with that green design, right? Where you are trying to do something, perhaps on the Verilog design, and there's some optimization or tweak or some transformation you want to do. Now, guess what? If you have a single design, it doesn't have to even be Verilog. It could be static chisel. And it's a really simple transformation. Guess what? Just directly modifying the design, that's the easiest thing to do. However, if you're directly modifying the design, at some point, as you want to do a more complicated transformation, it's going to be a lot of work, right? A lot of copy-paste. Perhaps you're writing a graph script. It's going to blow up in your face. And as it gets more complicated, it gets more hard, perhaps even impossibly hard. So what can you do? Well, this course I've been extolling the virtues of generators, which, although for a simple transformation have a much higher barrier to entry, once you want to do a sufficiently complicated transformation, it is going to be easier to implement, right? However, even for a generator, at some point, it's going to blow up for you. It's going to become a problem. And the reason why is you're trying to write all this Scala code to handle all cases, and it's kind of tricky. And so instead, it's actually easier, and what we're talking about today, to do a custom transformation. That is to say, you know what? For a certain amount of complexity of transformation I want to do, it's better to generate the design, and then once the design exists, go in and modify it the way I want to modify it. Cool. So now's the meat of the lecture. Hardware intermediate representations, right? So an intermediate representation, IR for short, is a way to describe what you're doing. And so this comes from the programming languages community. This is how they design programming languages and compilers in particular. And what it is this, the representation of how you express the program, and that representation can be used in memory or on disk for storage. But there's a few key aspects of it. Number one, has a well-defined semantics and well-defined syntax, right? You want this to be unambiguous and clear what all of these particular entities mean, what fields they have, and that sort of stuff. Because I'm a graph person, I like to think of it as a graph. But not all IRs internally are actually represented as the graph, but for today, you can think of it that way. So you can think of, oh yeah, I have a particular hardware circuit like an adder, and so the adder is going to be perhaps a node in the IR. And that's great. And so why do it this way? Well, this is a best practice from the compiler PL community. By using an IR, it makes it much easier to write these tools where, if you're just trying to think of writing a program and you want to say do loop unrolling, you're thinking about loop unrolling and parsing C at the same time, that's going to be really freaking hard, right? Now, if instead you have a proper compiler flow where you have the front end of your compiler parse the C and make sure the C is legal and actually turn it into the IR, and then later on, if it actually gets down to the point of you trying to optimization, like let's say loop unrolling, and you're working on the IR, it's much more constrained, much easier to work on that stuff. And so this is the best practice in the compiler PL community that hardware is now adopting. And it wasn't always that way, right? It used to be more monolithic. It used to have just these super complicated, unspecified internal data structures, and that caused all sorts of challenges for writing tools. And there's been a recent push to use IRs, and oh my gosh, it's led to a lot more new hardware tools because the IRs make it much easier to kind of develop this stuff. It's a much better software engineering technique, and it makes it a lot better. So as a result, now making a hardware design tool, any part of the flow, especially this kind of stuff involving the actual designs, much easier to make one, to modify one, to augment it, to add your own transformation, reuse, etc. Right? And so let's say you have an existing hardware flow that has an IR, and there's some scenarios. Like let's say you want to add an optimization. Great. All you need to do is write a pass. You can reuse the rest of the code for loading a design in, processing it, optimizing it, and also spitting it back out at the end. You just write a pass in the middle of the optimization you want. That's all it takes. So in other words, you can reuse all the other code. You just got to focus on the thing you need, right? Or maybe you want to write your own language. Maybe after this course, you say, you know what? Chisel's great, but trust me, I know the right kind of features I want users to be thinking about. Great. You can write your new language, and what's called a front end. And then the front end takes your new language and produces the IR, then you can hand it off to the existing tool flow, and you can reuse all that, right? So in other words, you don't have to write a super optimizing flow because it already exists. And this is a best practice from the compiler community, right? For example, LLVM exists, right? Initially, it was used for Clang, right? The C language compiler. But a lot of other languages say, you know what? That's a great compiler framework. So let's go ahead and write our own front end and then piggyback on everything else that already exists, right? So things like Rust or Swift, they're LLVM front ends, but then they use the rest of LLVM to actually do the compiling optimization. They can take advantage of all that expertise and coding has already been done, right? So same thing for hardware, right? If you want to write your own hardware language, write a new front end. Use existing IR and existing flow, and that's great. Or alternatively, maybe you want to make a new target. Maybe you have a different kind of FPGA you care about or something else. All you got to do is make a new backend. And everything else that IR comes from, would be all those various languages, optimizations it has, you can support, right? So as a result, having this IR abstraction really lets you kind of go into a tool and make the parts you want while using a lot of other parts. And so, like I said, the hardware community wasn't as adept at software engineering, so they weren't doing as much IRs. There were things that looked kind of like IRs, but the key difference was they weren't really specified, and more importantly, they were secretly internal, right? So a given tool might have an IR, but it wasn't open source and available to others to use. And it turns out that by specifying your IR carefully so that others can understand the rules, and also externalizing it, meaning external people can see the code, interact with it, and also inject things into it, that's the key enabler that's happened in the last couple of years. It's really been awesome. So here's a hypothetical tool architecture. I didn't label that middle box, but that's just to give you a sense of what could happen, right? So imagine that middle box is your hardware compiler flow, right? So you have some sort of IR. You have various transformations, optimizations. So how does this all fit in? That's the middle end, right? Well, to support different languages, you have front end. So like a front end per language, for example. So maybe one for Verilog, for Chisel. LNAS, this particular format here is Santa Cruz, PyRTL. Like I said, maybe you can language of your own choice. It goes through this middle end. Eventually, it can be turned into various things. Perhaps you want to turn in Verilog that's specialized for an ASIC versus FPGA. Perhaps you want to make a Swift Plus for simulator. Perhaps you want to spit out LNAS with one of these languages here at Santa Cruz or some other target, right? And like I said before, if you want to make some new transformation, well, you can leverage all this code, and then you can just write transformation you want, and you still get advantage of all these different inputs and all these different outputs, right? So this is kind of a really cool use of abstraction here to get a lot of great reuse. And the IR is kind of, you see in this picture, drawn very deliberately, the center of it all, right? Having that IR is kind of makes this all possible. Okay, so what do we have for IRs and Chisel? Well, we have Fertile. So Fertile stands for the Flexible Intermediate Rotation for RTL, or Fertile. And you've been using it all quarter without knowing about it because it's under the hood. But oh my gosh, it was a huge breakthrough, right? So before Fertile, so Chisel 2 and before, the Chisel code base was monolithic, meaning it was this really big, complicated flow. And if you went in there and to go change something, you would understand so freaking much. Everything was so brittle. Like you change just one little part in one place, even if you're bringing something else someplace else. It was extremely high barrier of entry if anybody contributed to the project. There was bugs in there. It was hard to test. So one of the challenges of having this giant monolithic code base is that it's also hard to test. It was a real problem. And so when people rewrote it for Chisel 3, they broke into this more traditional compiler flow where it had a Chisel 3 front end, Fertile is the middle end, then various backends, initially just the Verilog backends. That was a tremendous boon, right? That allowed a lot of things to happen. Number one, things are much more correct, but as time went on, they were able to really improve Fertile, they were really able to improve Chisel, and enable the whole world we live in now. And the result of this, between various software engineering choices made, including using this IR, it's a pretty reasonably correct code base. It's not perfect, there is the occasional bug, but it's pretty rare these days. And if you look at how small a team is supporting this language, that wouldn't be possible otherwise, right? If you ever use a commercial Verilog-based tool, you spent any amount of time on it, you found a bug, right? So having these IRs makes it much easier to kind of develop and maintain these code bases, and so Fertile's been really a godsend for us, right? So you hear me use the word Fertile, and both me and others, when you hear that term, it's actually referring to multiple things, and based on the context, to figure out what it means. So number one, Fertile is a specification, right? It defines the IR. These are the types of elements. Here's what they represent. Here's what their rules are. Fertile also represents to your hardware design in the Fertile format. You may have seen these .fir files floating around this course. And, well, guess what? There's also a Scala library called Fertile that, processes this Fertile, right? So all the above is true. Question, yes? Mm-hmm. That's a great question, and I'm going to be very clear to put it on going internet recorded that I can't fully answer that question, but my hypothesis is yes, it's definitely being done somewhere in the compiler. I suspect those memory safety checks are being done in a way that either builds on top of LLVM or has perhaps even been upstreamed in LLVM. There'll definitely be checks within the compiler. Now, technically, if you call them, checks in the middle end that were added on, you can augment the middle end. It's not required to only be a black box, or whether they're part of the front end for Rust, I can't say for sure. But yeah, definitely done by compiler. And same kind of thing. Like if you want to do memory safety checks, that's much easier to reason about if you already have the program digested into this IR form and you can see what refers to what and that kind of stuff. Cool. Other questions? So Fertile's been pretty awesome for the Chisel ecosystem. So how does it fit in? Well, the top flows, one I showed you in the beginning of this course, and that's been true all quarter. Our Chisel design goes in, which is a Scala program. So technically our Scala program, is compiled by a Scala compiler, runs the program. While it's running the program, the Chisel front end spits out Fertile as your hardware design. And that Fertile is then passed off to the Fertile tool, which then turns out in the Verilog if you want Verilog, or if you want to simulate, it goes straight from Fertile to Treadle, which is a Fertile-based simulator. That's the flow we've been using all this time. Part of why we say Chisel 3.6 for this course is this is the boundary between the new world and the old world. There is a new world coming. Not even coming, it's already here, I should say, in which there's still the Chisel front end. The hardware design is still turned into Fertile, but now the back end's different. Before it was inside what's called the Fertile library. Now it's in something called Fertool. Phonetically very similar, but not the same word. But it's a very different code base. So this code base is a Scala code base, much in the same spirit as Chisel 3. Fertool is based on a different IR called Circuit, which I'll come back to at the end of today's lecture. This is written with Plus using LLVM stuff. And so the reason why they're doing this is it's a lot faster and a lot less memory than the Scala-based stuff. But as a user, it doesn't look too different, right? Chisel goes in, Verilog goes out. I'm just showing you just to remember, let's say you wanted to write your own Fertile transformation. This is where your Fertile transformation happens before the Verilog backend, right? Perhaps in the middle, right? Using the Fertile library. But, you can imagine writing a circuit transformation and doing something similar. Cool. So what does Fertile actually look like? Your hardware design is turned into these components, right? And so there's a hierarchy of things or entities, right? If you want to not use overloaded term objects, right? So the top level organization is a circuit. Circuit, of course, is composed of one to many modules. Of course, modules can have nested modules. You can have multiple instances of the same module type. Now, of course, modules have ports. Inputs, outputs, the IOs. Yes, we know about that. A statement is the interesting one. That's basically what you think of as a line of Chisel, right? So like A connected to B, that's a statement. So statements, of course, can have more statements. So there's situations where you have like a block of statements, in which case that's why the statements inside statements. Statements internally are composed of expressions. So when you say things like A, and A is a Chisel object, that's a reference to the Chisel object A. Or, for.u, that is a Chisel literal, that's an expression. So statements are composed of expressions. Expressions can have expressions inside them, right? You can have A plus B, and then do the CAD that or something, so it keeps building up on top of it. And of course, all of these things use types. So this is an object type hierarchy diagram, but gives you a flavor for the kind of things there. And so, yeah, I kind of give you a visual representation of the prior slide. Like I said, circuits at the top level, modules have ports, and then statements and expressions are actual meat. And then, of course, you have types and ports. Questions so far? So let's actually write a simple module, right? So here we're calling this delay, which is really just instantiating a register. Super simple module, right? So we can even do Verilog first just for fun. Great. There's the Verilog. We've all seen this all quarter, right? Input, output. This time the gratuitous clock and reset aren't gratuitous. They're actually needed. Pause edge clock, this one for a register in most CAD tools, etc. All right, so that's print Verilog. What about the Fertile? How does this look as Fertile? Not super crazy, right? So, like I said, the top level thing for a Fertile design is a circuit. Then there's a module. That module has the number of ports. In this case, we have an input clock. It's actually a type clock. There's actually a clock type in Fertile. We have reset, which is of type uint, 1 bit. And then we have the IO, which even though it's labeled output, you can see some of these fields are flipped. So the input is still actually an input. And yeah, it has a 4-bit uint input. There's a 4-bit uint output. These braces indicate it's a bundle, which we learned about. So it's kind of it showing the grouping together. Then the register itself is a reg, and unlike Verilog, in this case, reg and Fertile actually means for sure register. And we can see it has a name. Here's the type associated with it, and then here's the clocking information. It's using clock and reset, and its output is IO out reg. And you can see, we can go ahead and feed that value from IO in, and then the IO design gets the output register, right? So this is the same thing, just now in the Fertile language. And at this point, it looks a lot like, not just the Verilog, but also what you expect it to be, right? And that's kind of the point. So Fertile was chosen very carefully to reflect things that only can exist in hardware. There's not many things in Fertile that are unsynthesizable, right? It's supposed to be directly things that are hardware. Um, it's also concrete, right? In Chisel, we can write generators where we know how many things are inside there. Well, it depends on the parameter, and you have to run it and see what happens. By the time the Fertile exists, the Chisel program's already run. The design's been elaborated, so that's a concrete thing. It's not a question of going to have 2 or 4 modules. The Fertile exists. It tells you how many modules there are. It's already been written out. Cool. Questions so far? Okay, so given that, what can we do playing around with that? Well, we can, dig into that Scala Fertile library and, instantiate our design, get the Fertile from it, and actually look at some stuff, right? So, for example, here is the Fertile as an AST or abstract syntax tree, which is perhaps a more clear declaration. So here it is, it's a concise bit of Fertile, but perhaps it's more clear looking at it actually as the various modules and case classes that compose it, right? So yes, there's a circuit. Here are the fields in that case class. For example, it has a list of modules. The module has a delay. Here's some of that metadata we talked about, things like what line it came from in the Fertile. Oh yeah, here now we have the ports, right, which is also a list, clock, reset, the I/O. The I/O is a bundle. It keeps going. I don't know why it cut it off. Maybe it's better if I let it actually print it properly. And yeah, we see if we print it out properly, oh my gosh, it's unreadable. So maybe it's better if we actually use this stringify tool. And now it's much more easy to kind of navigate it. You see the various parts of it. And you can say, yeah, there's a connection, from the output of register, taking in the input from the I/O, connects the I/O output to the output of register, etc. Questions? Yeah. Oh, great question. So what the heck are all these unknowns? So Fertile has some metadata in there, right? And so when it comes to this particular type, this is referred to as a reference, meaning you're referring to anything that exists in the design. This particular execution, the reference has the name it's referring to, but the type of the thing it refers to, its kind, and the flow direction are at this point not known. Now, I'll emphasize the key thing of at this point, Fertile, as it runs, kind of keeps getting more and more information. So you have to forgive me for not remembering exactly at which point we are at this point in this flow. I think at this point we're pretty early on, right? You can see that we've, gotten the Fertile for this design, but we haven't really fully processed the Fertile. We just generated it, but there's a difference between the initial Fertile and the final Fertile. And so some of these things that are currently unknown are going to be determined as the Fertile keeps processing. Yes. Exactly, yeah. So question, does that mean it's a multipass compiler? Exactly, right? So the initial Fertile comes in, is referred to as high Fertile. We'll cover this in a few minutes. And then over multiple passes, we lower that Fertile to low Fertile, and the things that are unknown become known. Ooh, how many passes does it take? It's not a simple number. It depends on the optimizations you have turned on, but we're talking dozens, which is part of why the Scala one was kind of slow. But I think the new one still does a lot of passes. The philosophy is to do a lot of passes because you can make each pass small and simple and single purpose. Now it's kind of easy to get them correct and easy to test them, and easy to turn them on or off. But you can imagine for performance reasons, if you can do multiple transformations at the same path, it will be faster, right? So it's kind of this compiler complexity correctness trade-off, right? Great points. Other questions? Oops, I can go back. So this design that we just looked at wasn't totally random. It actually came from the paper introducing Fertile, which I've linked here. And they also have a diagram in there, which I've reproduced in our courses format, but it's the original diagram, of course, is in this paper. And it just shows you graphically what's going on. So I'm a graph person, so I like seeing graphs represented graphically, right? So here we have a delay module, and we see, oh yeah, the ports clock in, out, right? And here's the types they're associated with. the statements inside of the delay module, which is a block. We instantiate a register, connect the register R to the input, connect the register also to the output, etc. Right? So you see that what looked like very simple code turns into this big thing. But this big thing, despite being a big thing, uh, is still easy for other tools to process, right? You can imagine writing code that traverses this graph and changes around these node types as needed to do certain things. Cool. Other questions? So now back to the nanopath question. There we go. Um, so yeah, when I said Fertile lowers, what do I mean? So as we described, Fertile is a multi-pass compiler. So um, it's all about making this correct and easy to test, right? And this is another good practice that came from the compiler community, is multi-pass technique, right? So rather than trying to take design from the Fertile comes right out of the Chisel front end and immediately turn into Verilog in one go, we're going to keep making this problem easier. And so what we're going to do is sort something called high Fertile. So high Fertile is basically what comes out of the Chisel front end. Technically, there's something called Churtle, which is even higher level than high Fertile, but forgive me for not talking about that today. But basically, at this point, it's like what you're describing in Chisel, right? So a lot of times in Chisel, you can do things where you don't specify bit width because they're going to be inferred, right? So that's what you're going to get. And then, of course, to actually emit something like Verilog, you can't just tell Verilog, hey, buddy, trust me on a bit width. No, Verilog wants to know a bit width, right? And so that's going to need to be known. And so an example of one of the transformation passes that goes on in the middle is actually inferring the bit widths, right? And as we know, if it can infer the bit width, it's going to tell us it can't. We're going to find out. So these transformations aren't just about changing the design. They're also checking the design, and then they need to convey when things are wrong. And that's a common challenge, actually, is for these internal transformations, which may discover something is wrong midway, simply telling the user it doesn't work, is not very helpful. And giving good feedback in the middle of a compiler flow is tricky to associate back to the original input. The Chisel Fertile world tries to track which lines of code things came from. That's not a perfect science. It's always room to improve. That's one of the things they've been improving a lot more to recent versions of Chisel and the new circuit-based flow. But like I said, the high level is just we keep lowering design. This very squishy, all things possible Fertile, and then we get down to a very concrete Fertile where everything is really, really similar to Verilog. And what's interesting about this is actually the way it's specified. This low-level Fertile, or low Fertile for short, is actually just a subset of the Fertile language. So when you look at the Fertile spec, anything that's possible, that's high Fertile. As you lower it, there's actually additional constraints placed on it. So if low Fertile is a subset of high Fertile, and by the time you're done low Fertile, like I said, all bit widths are specified. There's certain operator types that maybe in high Fertile you remove. For example, whens you can do in high Fertile. By the time you get down to low Fertile, they've been turned into muxes as needed. And it's like the lowering process isn't just about going from these high level designs so you can actually turn into Verilog. It can analyze your design for certain properties. You can optimize it. Maybe you want to instrument it in certain ways. Maybe you want to do things like add a scan chain or something, specialize it, etc. Other questions, comments? Yes. Oh, so where does that print Verilog I'm using this entire quarter come from? I can peel back the mask right now. So we go digging around inside of our here. So this is .sc. This is what actually been powering a lot of things for this course. So SC is this almond language, which is like making Chisel more scripting like. Come on, you know what this is. You want me to tell you it's Scala? You know this is Scala. Okay, so this is the thing that powers this course. This code has a number of contributors, so it's not just this course. The early versions came from Berkeley. Over the years, we've added things in the course here. But yeah, so what do we see? So for example, let's say something like print Verilog, which we've been using like crazy. Well, print Verilog is actually just print line called on get Verilog. Okay, what's get Verilog? Okay, get Verilog's up here. So get Verilog takes in a module, and you see actually what we're doing is we're calling a tool with some flags. So we're telling, hey, Chisel compiler, emit the Verilog. So yeah, when you tell the Chisel compiler to emit the Verilog, yes, it's actually going to trigger the Chisel front end and use the Fertile tool, the Fertile library, to actually lower design all the way to Verilog. We're giving it these arguments. Now, if you look at the actual Verilog that comes out of it, every line is a comment that tells you the original Scala it came from. I found that very distracting for this course. And although there are ways to change the passing of metadata within the Fertile tool flow, the most expedient way was to simply just make this function remove all comments, which looks for a certain magic string and then just simply drops it. So that's how come we get the nice tidy Verilog in this course. Yes, questions? For which one? What is going on here? Yeah, great question. So this is a Scala thing. Um, this syntax is telling you that it wants a delayed evaluation of the input. So normally in a function call, you evaluate all the input arguments and then call the function on the outputs. This is when you have that be a function, lambda, as you're saying. The reason why is we don't want this hard design to exist quite yet until we're ready for it, in which case we pass it on over here. So by doing it in this arrangement, for example, like let's say something goes wrong, if we didn't do it this way, and let's say the generation of your chisel caused an issue, we would not be able to catch the exception, for example, right? Because the exception would be triggered in the calling scope. In this case, by wrapping it and then delaying the evaluation until here, now we're inside of a try-catch scope, for example. So there's a few cases where, yes, you do need to have this kind of delayed evaluation of your input rather than doing it directly. And you have to forgive me for remembering the fancy compiler term for why you want to do that. But yes. Yeah, so anyway, so we've been using print Verilog all quarter. There was a get fertile. I didn't bother making a print fertile convenience thing. The stringify stuff came from the Berkeley folks. The visualize I used in the second lecture, if you remember when I showed the the diagram tool operating, right? That was from here, also from the Berkeley folks. This is code I wrote in a prior quarter, which I guess I never demonstrated, but it can do an embedded waveform in the notebooks. The reason why I'm not shipping that or pushing it is the result is unsatisfactory. Like the text height and like spacing, it's not good. So maybe someone who's CSS talented will look at this and get inspired. Thank you, internet. Pull request welcome, and help us fix this up, right? But yeah, here I'm using some stuff from WaveDraw. You know this guy over at Sci5. He's made a lot of waveform viewers. So he has one that's easy to call via API, and so I've done here. So yeah, these are the things kind of looking in your notebooks all quarter. Cool, great question. Let's go back to this, right? Yeah, so fertile lowers things gradually. We talked about that. Cool. Other questions? Okay, so to give you more sense for what goes on inside this kind of tool flow, I'm going to toss out some example passes, right? So things that are lowering passes, making it go from high fertile from the chisel front end to something closer to Verilog, as I said before, things like inferring widths, that needs to be done. There's actually also a pad width transformation, which is, let's say you're doing an add on two things at different sizes. That's allowed in chisel. However, for consistency, making it simpler for downstream, what if I pad the shorter one to be equal to length of the long one, so that way you're adding two things of the same size? As I mentioned before, expand wens. You have a when statement perfectly fine in chisel, but it's not a thing in Verilog, so we need to turn those into muxes and appropriate things. And so in addition to lowering the design, there's also a lot of safety checks going on, right? Making sure this is, okay hardware, no combinational loops, etc. And so depending on the checks that are being done, there are some being done in the chisel front end. There's a lot of them being done in the Fertile library. In terms of optimizations, some of these are maybe things that you can imagine or would actually even for sure find inside a conventional compiler, things like constant propagation, right? Where if you say, hey, val x equals 4.u and then use x a few places, by placing the literal in there, you actually will simplify the logic some. It'll try to do that when it can. Things like dead code elimination, as we know, it'll prune things that aren't connected to an input or output. Or CSE, common subexpression elimination, right? Where you do the same thing that's repeated, it recognizes that and tries to simplify things. These are just a handful of examples. Cool. Other questions or comments? Okay. So then, to give you a flavor of what's possible, now that you have this hardware AI available to you, what kind of cool stuff can you do? Well, there's a few things you can do. So I would say the poster child, beyond the chisel fertile flow itself, is something called FireSim, which is a really freaking awesome project where you can take a chisel design and just put on FPGA to run for simulation. But the thing is, in order to get the simulation you're doing, it's actually doing a lot of really cool stuff under the hood that makes something possible that wasn't really possible before. And that is, as you've experienced in this course, if you run a large hard design for a non-trivial amount of time, simulation is really, really slow. Now, of course, using FPGA is a lot faster, but there's some challenges, right? In particular, your design you're simulating has some notion of time, right? You know, whatever cycle means for it. That's not necessarily going to be the exact same frequency you have on the FPGA, right? And so as a result, you know, if you just simply take your design, check on FPGA to emulate, that can emulate your design, but don't simulate your design. So what FireSim does actually is it understands what time means, and it'll do the appropriate modifications to your design to create a modified design that goes onto the FPGA that correctly reproduces the right time. So if you want, you know, the effect of your design being, let's say, effectively a 2 GHz design with a, you know, 400 megahertz DDR memory, you can tell that, and it'll do the right delays, installs, to make that happen. So it's actually changing your design in non-trivial ways to make this happen. And I said this is even conceivable or doable because they aren't modifying arbitrary things; they're modifying these fertile IR graphs. So that was, you know, a research project by grad students at Berkeley led by Sagar Karanakar. It has a lot of additional cool things. You want to check it out. For example, it was designed to simulate an entire, you know, cluster from a data center. So you can use multiple FPGAs to simulate multiple stuff, but it does all the timing correctly, right? Imagine trying to simulate data center, you think about things like what about the network latencies and all that kind of stuff. All that timing and modeling and pausing and restarting, et cetera, is handled by the tool flow, right? So you just write your design the way you think it should be written. Under the hood is modifying design and insert the appropriate stalling and buffering logic to do all that stuff. So that was the original FireSim, which was awesome. Then it was taken further by optimizations called Golden Gate, where say, you know what? If we know there's certain properties of design, perhaps, for example, like I have multiple instances of the same thing, why don't I be more efficient on use of hardware? So rather than having 4 distinct cores using, you know, 1/4 FPGA, why don't I, you know, use 1 copy of the instance and then have 4 copies of its data? And then time multiplex, that is, you know, different cycles, different versions of that. And so the optimization is being done by a Fertile tool. So it's actually pretty cool. So you're able to write some Fertile to do this transformation optimization. To do that without Fertile is like basically unimaginable, at least from the point of view of academic person power, right? But with Fertile, that's totally possible. It's been done. And so what's been fun is it's allowed people to focus on what was cool, what they're trying to do. It was a really, really big enabler. So these are 2 often awesome examples. We have another one coming up next, but I'm going to pause for any questions so far. Okay, so then, oops, I'm going to fix this real quick. Excuse me. Added a new slide, but I forgot to make it a slide. Okay, so Essent, which is, you know, I'm biased. This is a tool that I originally made, and now my research group here has greatly enhanced. It's another Fertile user, right? So what is it? It's a simulator. And what's fun about this tool is we're able to explore simulation techniques, and we're able to be the fastest cyclic simulator out there in software, right? So FPGAs are fast, but if you're actually using CPU to simulate your design, we're by far the fastest, right? And so how is that possible? We have more sophisticated algorithms for what we're doing to your design than would be possible. And the thing is, because we're able to use all this abstraction, all these powers, right? You have Fertile to kind of easily process design. So from our point of view, writing this tool is actually not that hard, right? Using the chisel and Fertile to generate the design and actually give us Fertile, using the Fertile library to load design in, pre-process it, optimize it, etc. All I had to worry about is how I wanted to change the Fertile to do the things I wanted to do, and then how to turn that Fertile into C++ code. So when this simulator runs, it takes your design in, C++ code, you should then compile to be a fast simulator. So as a result, we can do some pretty cool algorithmic tricks. And so, like I said, this is the fastest thing out there. It's at least 2x faster than Verilator. Now it's even faster. We've had some recent work where now it's parallelized, so we can do multi-core output, so it's even faster still. And what's crazy about this is that it's about 5,000 lines of Scala we wrote, and we're competing against Verilator, which is, you know, the commonly used open source Verilog simulator, which is over 100,000 lines of plus code, right? And despite the 20x difference in line count, we're doing more sophisticated transformations, right? So how is that possible? Fertile, right? Fertile's taking care of a lot of stuff for us. So that line count I told you about does not count Fertile. Fertile, I don't know, about recently, a couple of years ago, I last counted at 10,000 lines, but that's 10,000 lines somebody else wrote that we get to reuse. But additionally, it's also a combination of using Scala, right? That like, don't worry, I'm very familiar with how to write this plus code. I do that for high performance computing all the time in research. But in this case, the productivity advantage of Scala is just too hard to deny, right? We're able to explore a lot of cool opportunities and we do some really cool transformations through design and make it really fast when simulating. Cool. Questions? Okay. So then, despite me giving you all this hype about how awesome Fertile is, it's on thin ice, which I'm sad to say. That's why I'm trying to make a strong case for Fertile. So why is it on thin ice? Well, the next frontier, which next is maybe not needed anymore. It is the current state of affairs. It's called Circuit. So it's a project that was started a couple of years ago and it's now become mainstream. It is not just simply an IR. It is actually an IR plus associated code base, and it's pretty heavyweight, right? This is a big thing, right? So it was originally started by some folks at Sci-Fi, but they have people outside Sci-Fi now contributing to it, and they're leveraging the code base and organization from the LLVM Foundation, right? So it has that kind of strong C++ backing. So how does it fit in? Well, it actually supports a lot of different hardware languages. The motivating design for this thing was to go from Fertile to Verilog. That was the motivating use case. But if you go to this webpage, which I should have a link to on the next slide, you can see it supports a lot of our dialects. So they have a lot of our notions of how to describe hardware, how to process it, how to think about it. In terms of what code is actually there and when it's actually commonly being used, Fertile to Verilog. That's the path people are using. But that's there. So you're saying, well, why does CMA exist? Well, the motivation for making this was recognizing, if you looked at the chisel flow, it had a very large design. The chisel front end wasn't that big of a time consumer despite being Scala, but that Fertile library doing all the processing and lowering became a bigger and bigger and bigger time sink for really big designs. And so by using Circuit, they're able to change over a new code base, take a lot of best practices and actual literal code from LLVM, but also C++. And so the result is quite a bit faster and uses a lot less memory. So now the current flow, so starting Chisel 3.6, you have a choice of which one you want to use, but after 3.6, you're forced to use Circuit. I can go back to that slide a few slides ago. It looks really similar, right, to the original flow. It's just, before this is a Scala program, now it's the C++ program. But internally it uses Circuit. So Circuit, as I said, it's using LLVM code base is a lot faster and nicer in that way. And so what's the roadmap? Well, the publicly stated roadmap is that the Scala-based Fertile library, sometimes referred to as the Scala Fertile Compiler, SFC, will no longer be continued to be updated. So as Fertile continues to evolve in the future, it's going to continue to exist as an IR, a way to link the chisel front end to what follows it. However, to actually process that Fertile, you're going to be forced to use Circuit, in particular FirTool is their tool that handles Fertile, but the Circuit handles many different languages. They keep processing it. And so, shed tear for Fertile. I'm still getting used to losing it in that sense. But why is Fertile still in the conversation at all? The reason why is as a spec, it's actually really good. And so if you think about a hardware design and you want to know, well, what do you keep as a durable replication of your design after you take something out and make a chip? Fertile's actually pretty good. Because if you have like a chisel design, to get the hardware design, you actually have to run the program, right? And unfortunately, anybody that's done software knows that if your program runs today, even if you change nothing about it, it may not run in 4 years, right? Something called bit rot. I don't mean the bits themselves are degrading. I mean literally the fact that the things you depend on and the world it depends on is changing underneath its feet, right? And I've been doing this stuff long enough, I can tell you this actually happens where you pull in a chisel design from a few years ago and, SFT is loading all the packages and all of a sudden it stops because there's some package it depends on which is not being compiled for the version JVM you're using or the version Scala you're using or something else, right? And so all of a sudden you're out of luck. Or even worse yet, in some cases, some packages that already previously were in their net get removed. And so they cull them. So what used to be able to build does not build anymore. So the result is a long-term durable format. Fertile is a really good thing to use. Because at that point, it's not just the generator, it's actually the concrete instance. And Fertile has well-specified semantics, right? It has a spec. It's versioned. And so the roadmap has Fertile continuing to be that interface. It's version to the spec is the long-term archival format to use for these designs. But for turning that Fertile into Verilog, Circuit via FurTool is the future, right? So uh, what can I say about writing tools in Circuit as opposed to the Fertile library from the past? The Fertile library in the past had a little bit of a learning curve, but it was very manageable. And if you knew Scala, really easy to get going. Circuit, different world, right? Now we're talking about the C++ LLVM world. So if you already know C++ LLVM, sure, Circuit's gonna be easy. If you don't know that stuff, there's some learning, right? And so depending on what your goals are, this is either a good or a bad thing. A lot of people were using Fertile transformations not to make standalone tools, but instead to just like tweak one thing about their design. Perhaps they had a design they were making and they wanted to insert a scan chain. That's the kind of thing you can do really easy with Fertile transformation to actually go into your design after it exists and put it in the scan chain. So like these kind of small one-off transformations, the Scala-based Fertile library, SFC, made that really easy. With Circuit, that's not so easy. With literally a standalone tool, Circuit allows you to do it, but of course then you gotta, imbibe all the challenges with Plus. So for example, I have a grad student working on this stuff nowadays, and they've done tools, multiple versions of tools in Essent with the Scala-based Fertile library. And now they jumped over to Circuit, and they've kind of noticed that there's some cool things about LLVM code bases, but of course also things like seg faults are now a thing again, right? Actually, they aren't a thing in Scala, right? So this is a very good programmer, but it's just challenging with perfect C++ code. There's always issues. There's some large binaries, there's some long compile times. It's not all roses, right? But this is still the way things are going. And, trying to be a productive academic, rather than fighting the current, you try to, ride the wave, figure out where things are going, and take advantage of it. Cool. So to kind of wrap up, hopefully get you excited about hardware IRs, right? It's a way to make, tools and do transformations. There's a lot of different hardware IRs. Like I said, there's the ones here, so Fertile's the one from Chisel World. There's other ones out there, right? And it's kind of this thing, they're all becoming kind of publicly out there, right? So Yoast is a tool you may have all heard of or used. Had its own internal thing, RTLIL. Stanford had a Core IR project, which now seems to be inactive, maybe, question mark, but for a while it was a competing IR standard. From ETH, there's LLHD, which is also being folded into the Circuit ecosystem as well. There's of course Circuit. There's many more research things, depending how you define IR. There's like, Calyx from Cornell. And then here at Santa Cruz, and Professor Renau's group, they have LNAS, or the Language Neutral AST for hardware, right? So there's a few things out there. Cool. Any last questions? Great. Okay, that's all, folks. So just as a, oops. Why is it?